So today we're going to start DC circuits, recurrent circuits. In terms of question volume or in terms of importance of this chapter, it is nearly as important as the kinematics chapter. Kinematics chapter means the chapter that handles with the motion, acceleration, and force, Newton's laws, equations of motion. Those that chapter. The amount of questions that we typically have from that exclusive chapter, which is a pretty big chapter, if you ask me, compared to the other chapters like thermometers or heat capacity or density, pressure, or work energy power. Kinematics is a pretty big chapter, and it actually has significantly large number of questions compared to other chapters. DC circuit is also a similar one. DC circuit also tends to have some questions which are quite large in terms of number value. I mean, and if you have a 15-mark question in your section B in your actual exam, uh, you can still expect some significant number of questions in the section A from the same DC circuit chapter. So we're going to be pretty careful in operating in this chapter. DC circuit chapter, in my opinion, if you ask me, it's actually quite fun as long as you understand how it works, because the underlying principle for how circuits work is actually quite small. The principles that govern the working of a DC circuit is actually quite small. It all depends on how smartly you actually can manipulate that for your advantage. Manoj is very much like a journey, like to go from point A to point B. There can be a lot of different ways. Through practice and through understanding, you need to develop the skill within yourself to understand that which of this path is gonna be the least time consuming and least effortful for my purpose. So that's what I'm gonna try to teach you for this chapter, among other things. So if we start directly from the very start, the first thing that we have a couple of definitions. The first thing is that current. By definition, current is defined as the rate of charge flow, I equals to Q by T. The unit is ampere, which is given by coulombs per second. Ampere is one of the base quantities. Coulomb is not. Ampere is one of the base quantities because current is one of the, ampere is one of the base units because current is one of the 7 base quantities. The definition of 1 ampere is actually given by a far more complicated manner than you can think. It's given using the terms of electromagnetism in terms of force. So I'm not going to give you that definition for the time, but if you're interested, you can Google this up. You just have to remember that current is a base quantity and in the ampere is a base unit. That's pretty much it. And one thing that we have also known up so far, we also have to see some more definitions. The second definition that we're going to talk about is what we call resistance. Resistance is basically the unwillingness for any material to allow free flow of charge or to allow current through itself. So that's the very basic idea of resistance. Unwillingness, I'm using the word unwillingness because unwillingness or hindrance can come from a lot of different physical properties. You can have shortage of free electrons. You can have the material being stuck, the particles of the material being stuck very strongly. In some cases, you can have electrolytic solutions. That's a totally different scenario. But the key idea of resistance is that the hindrance or the obstruction that any material creates against the flow of charge through itself. So if you're trying to create a flow of charge within an object, the opposition or the hindrance or the obstruction that the object tries to propose against it is what we call resistance. Resistance is a pretty basic idea. This was the qualitative definition for resistance. What just saying what resistance is. In terms of quantitative definition, we define resistance using Ohm's law. Now, to explain Ohm's law, I have to first explain what voltage is. So let me just get to the definition of voltage, and then I'll have to explain the voltage, and then I'll have to go to Ohm's law, and then I will give you the definition of resistance once again. Voltage, and we are gonna learn voltage and EMF at the same time because they are very close to each other, but they are not the same thing. They're very close, but they're not the same thing. Voltage and EMF, they both pretty much are a pretty important concept for you to understand, and you have to understand clearly that how does the voltage work for a circuit. This is one of the key concepts that if it is not understood properly, you would have a hard time handling circuits. You have to understand the concept of voltage very easily. Dealing with current is actually quite simple and easy, because for your syllabus you don't have to work with AC, you only have to work with DC, and you don't have delta or Y junction type of things. So observing the pathway for current from high potential from positive end of the source to the negative end of the source is actually quite simple. So current doesn't pose that much trouble for your level, but the voltage can do pose some trouble. So let me try to elaborate this in my capability as much as I can. The definition of voltage, if I just write the word definition, voltage is given by energy per charge. For the time we just try to understand this, energy per charge. Or we can also say this as work done per charge. Now, what does this entail? What does this mean? This essentially means that whenever charge will do energy conversion or charge will do some work, because energy conversion and work done, they are pretty much the same thing. Whenever a charge will do energy conversion or charge will do work, then the term voltage would be applicable. Let me give you a very simple scenario. The unit is like this. The unit for voltage is volt. It also comes from the name of the scientist Alessandro Volta. So V is given by joules per coulomb. So that's a very simple idea for voltage. 1 volt equals to 1 joule per coulomb. If you're trying to define 1 volt, you can pretty much say that 1 volt can be written as 1 joule per divided by 1 coulomb. So if you want to define 1 volt, it's pretty simple. You can say that if 1 coulomb charge does 1 work, or you can write if 1 coulomb charge converts 1 joule of energy into another form of energy, the potential difference is said to be 1 volt. So that's how we define 1 volt. It might sound a bit ambiguous because I haven't yet given you the idea properly. Let me just elaborate this thing. Voltage is a typical term. There are a lot of different terms that we can use against voltage. I mean, we have a lot of terms that can mean synonymously for voltage. We have potential, difference, voltage difference, voltage across 2 points, and voltage difference. So potential difference and voltage difference, they both mean the same thing. They're synonymous words. So you might come across either of these two terms whenever you are trying to handle the term voltage. What does this actually mean? Let me tell you a very simple thing. If you consider a battery, very basic chemical reaction battery. So any battery is typically consisted of 2 electrodes, and they are typically submerged within a certain chemical energy full electrolytic solution. These 2 electrodes are usually different metals. They are not made from the same metal, and they react with the solution, electrolytic solution. This is in many cases it is a acid solution. In some other cases it can be some sort of salt solution like ammonium chloride solution, or ammonium chloride paste. Even for dry cell we use ammonium chloride paste with a bit of a manganese dioxide, but this is a different issue. So we have a little bit of a gel or liquid kind of thing which is gonna work as our energy storehouse, and we're gonna have 2 electrodes which are made from 2 different metals. That's basically how a battery works. A very crude version, but that's quite how a battery works. These 2 materials react differently with the liquid solution over here, and as a result, one experience shortage of electrons. It means the solution somehow pulls out electron from this one, and it keeps on accumulating electrons onto the other one. The chemical reaction that these 2 electrodes do with the chemicals that is within this battery, that chemical reaction basically does this job. That's what you need to understand in the first place. The chemical reaction, by its own capability, accumulates electron on one of the electrodes and steals electron from the other electrode. So by default, this one is become positively charged, this is becoming negatively charged, and by naturally they would want to come back to their original state. So what we can do, we can take a piece of wire, and let's say we are gonna open a switch, and we're gonna take a piece of wire, and we can have them connected like this. As long as the switch is open, the charges cannot flow, electrons cannot flow. But if we just close the switch, electrons will immediately go from their high concentration place to their low concentration place. So in this case, electrons are going to flow out in this manner, and whenever we will close the switch, and then they're going to try to become neutralized. But if you ask me that are they going to be neutralized, the answer is in many cases no. And closing the two ends of a battery directly by a single piece of wire can actually be very, 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 very dangerous. I'll tell you why that is dangerous after a while. But just for the sake of making you understand the flow of electron and everything, I'm just showing you this example. But still, so that you do not take the wrong image out of this, let's say I'm gonna just draw a light bulb over here for the sake of explanation, because I'm gonna need a light bulb anyway. So if we have a light bulb over here, and if we close the switch, the electrons are gonna flow in this way. And as the electrons are gonna flow through this light bulb, they are going to spend some of their energy, or in other words, you can think all of their energy. Both of these words can have the individual significance. I'll tell you this in a bit. The electrons are going to convert some of their energy, or maybe all of their energy, into this light bulb, and eventually they're going to come out onto this end with zero energy, and they're going to flow through this thing, ultimately coming back to the positive end. That's how the electrons are going to flow by. So this is what is happening. The chemical reaction which is happening within this solution, or acid solution, or the electrolytic solution or salt solution, is responsible to separate the charges. So this is basically working as an energy reservoir. The chemical energy is causing the electrons to separate in two different electrodes. And whenever we're closing the switch using a bulb over here, electrons are allowed to flow through the bulb. And when the electrons are going to flow through the bulb, the flow of charge is what we call electricity. And when the chemical reaction is happening, it is still very much some sort of potential energy, because you have two objects in two different potentials. One is highly positive charge, and the other one is highly negative charge. But you still don't have any current, so we do not say this is still electrical energy. We do not say it's electrical energy. We say it's electrical energy the moment it is allowed to flow. The moment the electrons are allowed to flow through the wire, that's when we say that the chemical energy of the battery is starting to convert into electrical energy. So electrical energy is available at the two ends of the battery, but not until you connect it with the wire. As long as you do not connect it with the wire, it is still pretty much potential energy. And within the chemicals, we have chemical energy, which is also sort of like potential energy because it's stored energy. So that's one thing. Hold on, তোমরা কি আমার কথা বুঝতেছো না ঘুমায় যাচ্ছ? আচ্ছা, none of you asking me any questions, so I'm assuming either it's all making sense, or you don't care, or maybe you're bored because you know all these stuffs.
So I have a question.
Acha, if you have question, please raise your hand, or just ask me to re-explain something, or just make a casual yes sir every once in a while, just to that helps me if you feel like it. So electrons are allowed to flow through the bulb, and eventually, and when the electrons, because of this chemical reaction, there is significantly more presence of electrons, and there is a shortage of electrons, and that produces a potential difference between them. Potential difference basically means that there is a bit of an energy gap between this thing. Electrons are wanting to get back to this side to make the balance reestablished, and that tendency of going back will cause them to have some amount of energy with respect to this side. Now, whenever the electrons are going to flow through this wire, we say the electrical energy is being available because current is being created. And when the electrons are going to flow through this bulb, a bulb is typically an electric bulb can have a lot of different technology by which it is built upon. The most old version of electrical bulbs are filament bulbs. Then we had fluorescent bulbs, which is basically the energy lamp, and now we have LEDs. There can be a lot of in between inventions, but these are the most three commonly commercially successful models of light bulbs: filament bulbs, and then we had fluorescent bulbs, and then we have the LEDs currently that we use. Now, if you consider a fluorescent bulb, if you consider filament bulb is the most common type of bulb that we talk about in our DC circuit for your CIE O-level syllabus 5054, because filament lamps are easy to visualize and easy to deal with, and we know how it works. Fluorescent bulbs are also, the working of fluorescent bulb is also included in the syllabus, but we don't go for it that much high value because it has some voltage restriction requirement, and it requires some a bit more deeper knowledge. So consider this as whenever I'm going to say a bulb, I want you to naturally visualize this as a filament bulb. Although filament bulbs are pretty much not present anywhere in our house because we have nearly come over the age of filament bulbs, but I want you to imagine it as a filament bulb. Filament bulb is basically, there are two pieces of wire which are hard wire, and in between these two pieces of wire we have a very thin wire which is coiled and springed, and it is connected on the two sides. and we're going to apply some voltage across these two wires, and this whole thing is connected is placed within a evacuated or nitrogen filled glass, and this is the metal plate, and this is the pins, and here we have the two connection points, and these two wires actually flow all the way down here and can connect to the connection point. So whenever we put this into the socket and we apply the voltage, current will be able to go through this filament from one end to another end. Because this wire is actually very thin and very long, this produces a very significant amount of resistance because it is pretty thin, so it doesn't have it doesn't want to flow too many electrons through its cross-sectional area, and it's also pretty long, so it's a long wire with a very thin cross section. So both of these factors attribute towards a much stronger resistance, and whenever the electrons have to flow through this stronger resistance, they will have to spend their electrical energy to pass through that filament part. But if you but typically these filament lamps are designed in such a way that these supporting wires, I mean this one and this one, they're usually made from really good conductors, and they're usually quite thick. The aim is that we do not want the energy conversion to happen within these two wires. We want the energy conversion to happen within the filament part exclusively. So what happens whenever the current flows through this bulb? I'm not actually showing you any direction of current flow. I could, but if I just draw a bit of a battery, and this is a bit of a battery with a maybe a closed switch connected to it. This is a closed switch symbol, and in this case current is going to flow from positive to negative. So this is the conventional current flow direction, and electrons are going to flow the other way. So I'm going to show the electron flow with a external arrow. That's how it's preferred. The electron flow should be shown outside the circuit, not with on the circuit, and conventional current flow I should be shown on the circuit. I'm going to tell you what conventional current is in a bit, but I want you to understand this thing. Whenever electrons are going to flow through this part, they are going to spend the electrical energy within this wire, and that will heat up this coil and that filament coil, and that filament coil will now start to heat up and heat up and heat up, and as the object is going to start to heat up, it's going to become produce a lot of heat, and it will also slowly start to change color from orange, red to orange to even to a very bright white color, depends upon the temperature. So that's basically how filament lamp works, by primarily heating the filament lamp. Now, in this process of heating lamp, each of the electrons, the amount of electrons that the amount of energy that each of the electrons entered the filament lamp right over here. Let's say the voltage of this battery is 10 volt, which means that uh, it is 10 joule per coulomb. The physical significance of 10 joule per coulomb means each coulomb of energy, each coulomb of charge that this battery is going to let out from itself, each coulomb of charge that the battery is going to let out from itself are going to have 10 joule of energy within themselves. Now you cannot say, well, then how many of these charges can it produce? That can vary. That depends upon the size of the battery. One thing I would like to show you that about the size of the battery comparison and the voltage idea. Let me show you this thing. Have a look. These are the size of different type of batteries that are available to us in the market. Okay, so did I wanted to show you this? Okay, yeah, these are the size of the, this is the Resistor company battery. I'm not sure if they're gonna sue me because I'm using their image. Whatever, it's a free advertisement anyway. Not that I have a good YouTube channel. Anyway, the point is, apart from this rectangular battery, all of these circular batteries, they are all rated 1.5 volts. All of them are rated 1.5 volts. I don't know if 4A batteries actually exist, or I have never seen it. We have seen AAA batteries. We use the AAA batteries in many of our remote controls. This is the most commonly type of used battery in the remote controls. AA batteries are also we used to use them. We currently use them more commonly in our wall clocks or the alarm clocks or the table clocks. That those are the places where we need AA batteries. And C or D, I'm not sure which of these things are C and D. I mean, I know them as A batteries, single A batteries. Those are the batteries. Those are used in very long torch lights, like a long cylindrical one. We don't have them very commonly right now because currently everything is designed to be rechargeable. Lithium-ion batteries are actually quite cheap and widespread available for us. So these are the thing. But one thing you need to understand that each of these batteries, each of these cell are rated 1.5 volt. But how much energy do they contain is different. Each of these cylindrical battery has a voltage of 1.5 volt. If you wonder how is that even possible, it is possible to by smartly designing the object. One of the reason consideration, which you don't have to know for your syllabus, that I'm telling you, one of the reason consideration for how much voltage a certain battery is going to produce is basically is directly related to how much area or surface of reaction are you allowing. মনে করো এখানে যে আমাদের we have two electrodes over here. If I gave this electrode a certain surface area, I'm trying to show you a bit of a 3D image over here. Let's say this is the surface area for this electrode, and let's say this is the surface area for this electrode, and they're both submerged within a salt solution or within an acid solution. Now you have to understand this thing. If these two surfaces are big, then they are going to do reaction in a much more rapid rate, and that will enable you to be able to produce more joule of energy for each coulomb of charge. That is one thing that we can do. But if their plates are actually fixed amount of size, if the plates are smaller, then the rate of reaction would be less, which means each coulomb of charge would not be getting as much energy out of the chemical reaction, because the chemical reaction itself would have happened to be less. That's one thing. That's one of the factors that can control this thing. This is something that you don't have to know. I'm trying to give you some ideas so that you can understand the electricity thing interestingly and completely. And the other thing that can actually also affect is the concentration of this chemical that we use, acid or salt solution that we use over here. That can also lead to the voltage thing. But we can pretty much control how much the surface area or the concentration of this of the concentration of the acid to be by our choice. And if we keep these two variables pretty much same for all of these batteries within their construction, within the internal construction, we can design all of them to have the exactly same amount of voltage, which means each of these battery will produce, if they're already 1.5 volt, it means they are going to produce 1 coulomb of charge out of themselves, which is going to contain exactly 1.5 joule of energy, period. This is not going to be more, this is not going to be less, this is not going to be a variable. However, because the difference in size, you need to understand that the one that is big has a larger amount of this acid solution, which means this battery will be able to produce a big number of 1 coulomb charges, which will have 1.5 joule each. This one will be able to produce a far fewer number of 1.5 joule energized 1 coulomb charges. So bottom line is this will last for a longer, this will last for a bit less, quite a bit less, but they are all rated 1.5 volt. Why am I telling you this? Because I want you to understand that unless it is designed in a definitive way, typically batteries can have, irrespective of their size and shape, they can have the same voltage. Whereas this is something that we call the rectangular battery. Here they have named it PP3. I'm not sure if PP3 is the actual name. What is the name of the square battery? Do we call them square battery? Square battery. Okay, maybe they are called square battery. So this is the battery that we are saying, one isolated square battery. These batteries are designed to have a voltage of 9 volt. They provide 1 coulomb of energy, 1 coulomb of charge as it will come out from the battery to contain 9 joule of energy. So their rate of reaction / the concentration or the concentration of the acid or the electrolyte is far too higher compared to any of those cylindrical cells, because they are rated to have 9 volts, whereas each of these circular batteries, cylindrical batteries, were rated to have 1.5 volts. So that's the difference. You can design batteries differently depending upon how we are designing them. We can have different type of voltage outputs. The point that I'm trying to make is that the size of the battery is not a direct denominator or notion creating thing to tell you how much voltage should it have. It can have a lot of different value of voltage. In most cases, bigger batteries contain more energy, more chemical energy, and smaller batteries contain less amount of energy, assuming they are all made from the same technology or they all operate on the same chemical reaction with the same type of electrodes and everything. Obviously, you cannot think. I mean, if we could make a cold fusion possible, do you guys know what cold fusion is?
Sir. Sir.
Yes, sir, or no, sir?
No, sir.
Okay, fusion is the basic process by which the sun produces energy, which is the combination of hydrogen atoms into helium. In which process, it's a nuclear process where smaller particles are merged together to produce a heavier particle, and that simultaneously produces energy. And it is a very clean form of energy because it doesn't produce any of those radioactive pollutants or alpha, beta, gamma radiations. It's just energy and period. It's a good thing. But to achieve this process, we have to have a very huge amount of temperature available for the reaction environment. Like without an extremely high temperature, it is this reaction cannot sustain itself. It means it simply does not happen. You have to be continuously be able to maintain a very high temperature and also have the reactants and process present so that you can produce the product and have the reaction and energy given out from the reaction. These reactions are highly energetic, not in terms of one reaction, but in terms of the energy that can be made available from per kilo. So let's say the amount of energy, fusion energy that we could possibly get from 1 kilogram of hydrogen is far too big compared to the amount of energy that we could possibly get by nuclear fission of 1 kilogram of uranium. Similarly, the amount of energy that we could possibly get by burning 1 kilogram of methane gas, which is the most common gas in our cooking stoves in Bangladesh, is even far too less. Uh, so that's the idea of energy concentration, that how which one has the capability to give us more amount of energy per kilogram of mass or equal amount of mass. Now, cold fusion is an idea that it's still a theoretical idea. The idea is that if we could possibly make the process of fusion at a room temperature level. Now, if you wonder that doesn't make sense because it requires high temperature. Yes, that doesn't make sense yet, but maybe some scientists in the future may be able to visualize them better and be able to produce. The idea of cold fusion is that we're going to have fusion batteries. So they're going to be batteries. We're going to buy them. There might be some on and off switch. We're going to press the switch on, and the fusion will automatically start. And that fusion process will be contained and be sustainable within room temperature. And those batteries are going to live like till the end of this universe, because the amount of energy that can be stored within a very small battery that can be extracted out of fusion process can be extremely high, like super high. Even I mean, a little bit of hydrogen gas stuck with the fusion reactor can give you energy at 1.5 volt for quite a couple of eternities if you think about it. So that's the idea of cold fusion. The reason I'm telling you about cold fusion because is that, I mean, how much energy are we going to pull out from the battery? It depends upon our requirement. But how much energy did we put in the battery? It depends upon the manufacturer. If you want to have a long-lasting battery, you just have to go ahead and buy a bigger battery, or you have to buy a better technology battery for the same size. For example, we can have alkaline batteries for certain purposes. You might have a come across this term, alkaline batteries. We can also have lithium-ion batteries. We in some of the other type of batteries we have lead acid battery. So lead acid battery. So we can have a lot of different technologies over here. Alkaline batteries are the type of batteries which are more popular before the lithium ion rechargeable batteries came in the market, and they used to have a pretty significantly good amount of energy concentration. They were used in the celluloid cameras because 2 pairs of alkaline batteries could run a whole film of 36 images with the flashes and everything. And now we are using lithium-ion batteries. Lithium-ion batteries are also good. They are rechargeable. And lead-acid batteries are those which we use for the IPS things or in trucks or in the cars. They work in the lead-acid mechanism. So they have different purposes in different places. Why am I telling you all these stuffs? To give you an idea that whenever a battery is labeled as 10 volt, it means that it is producing 10 joule per coulomb. Each coulomb of charge that this battery is going to let out from itself will have 10 joule of energy within themselves. Now, comes the idea of generalization, or what we call approximation. The idea of generalization is that we're going to define something to have the least amount of complications so that we can explain it better, we can understand it better, and then over time we're going to start adding more complications to the system to make the system more realistic. uh, One of the simple example is that for all of our maths that we have done in our kinematics chapter, we have considered air resistance to be negligible. But to be honest, air resistance is not actually negligible, not actually negligible. But we did consider that for the sake of simplicity. Similarly, for this in an electrical circuit, there can be a lot of different electrical circuit components. Let me just show you a bit of a symbol. তোমাদের স্কুলে কি ডিসি সার্কিট কিছু হলেও পড়াইছে?
Yes, sir.
তোমরা তো সার্কিট সিম্বলগুলো কিছু কিছু কি জানো?
Yes, sir.
সবগুলা জানা?
সবগুলো না, লাইক অল্প করে মনে আছে।
আচ্ছা বলো তো এটা কি?
সেটা বাল্ব।
না, এটা বাল্ব
গ্যালভানোমিটার, এমিটার।
না।
সেকেন্ডটা তো বাল্ব না?
এটা বাল্ব,
হ্যাঁ
এটা গ্যালভানোমিটার, এটা অ্যামিটার। এটা কি?
লজিক গেট।
একটা কিছু বললেই হইলো। দেখাই দিছি, দাঁড়াও, টেনশন নাই। তোমাদের সিলেবাসের পুরো রিকোয়ার্ড সার্কিট লিস্টের যা তোমাদের ইয়াতেই দেওয়া আছে, সিলেবাসের পিছনেই দেওয়া আছে। সো ওইখানে খুব ইজিলি পাওয়া যায়। দেখাই তোমাদেরকে। If you go down to your syllabus, তোমরা হচ্ছে 2022 নো, সিলেবাসের পিছনে নাই। হ্যাঁ, আগে তো ছিল। আচ্ছা ব্যাপার না, আমি তোমাকে অন্যখান থেকে দেখাই দিচ্ছি। কই জানি রাখছি এটা। সো এটা হচ্ছে মোটামুটি একটা ফুলি কমপ্লিট লিস্ট। এখানে সবকিছু তোমাদের সিলেবাসের জন্য লাগবে না, বাট এখানে কিছু এক্সট্রা জিনিসপত্র আছে, বাট যেগুলো আছে সেগুলোর বাইরে কোনো কিছু হওয়ার পসিবিলিটি নাই। I want all of you to have a good look at this list and try to make sense, because we're gonna start drawing circuits in a bit. So it's better if you learn these symbols in the first place. Have a look. First thing, they're showing the conductor crossing with no connection. You can see that there is a plus sign with no nodule or no node at the center. Do you see that? They are just two wires placed on top of each other. If we ever have this kind of communication connection or in the circuit, we have to understand that these are disconnected wires. It means horizontal current will flow horizontally, vertical current will flow vertically, and there will be no, they are not connected wires. In physical terms, you can visualize that if we have two pieces of wire which are insulated to each other, they are simply laying on each other. We have not removed the insulation and made them into a joint. They are just laying on each other. That's the meaning of this symbol. First symbol. এটা বুঝছো?
Yes sir.
ঠিক আছে, no connection. And if we have connection, then we're gonna have this kind of nodule. এটা একটা ওপেন সুইচ, ক্লোজ সুইচ, ওপেন পুশ সুইচ। আচ্ছা, ওপেন পুশ সুইচের বেসিক আইডিয়াটা হচ্ছে যে এই পুশ সুইচ হচ্ছে বেসিক্যালি যে কলিং বেলের যে সুইচগুলো থাকে সেইগুলা, যে দেয়ার ইজ এ স্প্রিং বিল্ট ইন। সো if you have a physical intervention of pushing, as long as you are gonna keep the push on the switch, it's gonna be closed and the circuit will work. The moment you take your hands off the switch, it will be automatically switched off. That is not the case for typical switches. For example, if you think for the switches that we use in our houses for light, fan, TV, fridge, etc., they actually has two stable state or two fixed position. If you press the on, it will remain on there unless it is switched off by someone else. If you press it at off position, it will remain in off position. So it will not automatically switch back to the other position unless someone intervenes. So we call these type of devices to be bistable devices, where it has two definite position of operation, on and off, and they will not be automatically flipped back. Whereas a push switch is something that if it is built up with a spring, pretty much like the columnar switches. So if you press it, it is closed. The moment you remove your pressure, it is open. So it always prefers to go to the open state. It will only maintain the closed state if you physically intervene and push the switch. So these are the symbols for the push switches. Then we have a symbol for a symbol cell. A symbol cell is two parallel lines. In this case, in the case of printing, they usually use one of the line to be thinner, the other line to be thicker. Whenever you are about to draw this thing, you don't have to bother about this. Drawing two parallel lines, one longer and the one shorter, makes a cell. And what is important, that this is a cell, which means that this is only one unit of the battery. Battery of cells means there are multiple cells which are connected in a series combination with the same polarity. Same polarity means that you have connected plus minus plus minus plus minus plus minus like that. You did not connect them haphazardly. Minus plus plus minus plus plus. they have to be or connected in an orderly fashion. So that's the important bit. So that's what we call battery. More than one cell makes a battery. So if you have one cell, that's one cell, we use the term cell. If you have two cells, you can use the term battery. Here they have used the this is the symbol dot 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 dot. This dot 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 means there can be a lot of batteries in between. This is just a representation of continuum of what is on the left and what is on the right. That can happen, or sometimes batteries can also be drawn like this. Have a look over here. If you just draw batteries like this is also a very common way to draw batteries. Sometimes batteries can be also drawn in this manner. We give a bit of a connection wire, and then we draw another one, and then we give a bit of a connection wire, then we draw another one, and we give it a bit of a connecting wire, and then we draw another one. Sometimes batteries can be also drawn like this. Have a look at the difference in these two. Here, I mean, one cell is one long and one short. This much is one cell. There should be no connection in between these two things, because between these two electrodes, the long side and the short side, we usually have the electrolytic solution, acid solution, or salt solution. And so if you're trying to produce a series or an array of multiple cells, you better connect them across this part. So be careful about the connection part. So this is how batteries look like in circuit symbol, apart from this dot 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 symbol. And then we can have power supply. DC power supply will come with circles. In electrical circle, in generally, if you have a symbol like this kind of a round thing, this usually means this is a possible connection point. This is a possible connection point. It means if we have a situation like, let's say there is a certain point that says that, well, we have a situation like this, and this is a plus, this is a minus. Now we have to connect a light bulb. So this means that these two things are open ports where we can attach new wire conveniently, pretty much like the plug of our in our houses. I mean, I told you did I tell you the difference between plug and socket?
No, sir.
তোমরা কি জানো প্লাগ এবং সকেটের মধ্যে ডিফারেন্স কি?
সকেটে অনেকগুলো প্লাগ থাকে।
না 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 ইলেকট্রিক্যাল কানেকশনের সময় আমরা যে জিনিসটার মধ্যে আমরা কানেক্টরটাকে এন্ট্রি করাই সেটা হচ্ছে সকেট, আর যে জিনিসটাকে এন্ট্রি করাই সেটা হচ্ছে প্লাগ। ফর এক্সাম্পল, আমাদের টিপিক্যাল সব ডিভাইস, মোবাইল চার্জার বলো, তারপর হচ্ছে পিসির কেবল বলো, মশা মারার ব্যাটারি চার্জার বলো, এই সবগুলোর মাথায় হচ্ছে দুইটা পিনের বা তিনটা পিনের একটা মাথা থাকে, যেটা আমরা দেয়ালে একটা সার্টেন এবোনেট বোর্ডের মধ্যে ঢুকাইলে সুইচ দেওয়ার পর জিনিসটা চার্জিং শুরু হয়। So the wall mounted thing is what we call the socket, which takes in the product, the plug, and the one that we put in the socket is what we call the plug. That's the difference between plug and socket. Socket is the welcoming one, and plug is the entering one. বুঝছো?
Yes, sir.
ঠিক আছে। So plug আর socket কথা বলতেছি এই জন্য যে these two are pretty much similar, like the socket of this thing. এখন আমরা যদি if we want to use this DC connection for operating some electrical device, we can simply pull out some wire and we can connect a cell over here, bulb over here, maybe with a bit of an open switch, and we can complete a circuit over here. This is a fully complete circuit. Now, one thing you have to understand, you might wonder, this is an open circuit. We do not see anything connected to these supplies anymore. I mean, how does this circuit will work? That's the key idea. Whenever we are given a DC circuit that looks like this, a plus or minus, so it looks like this, two circles which are labeled plus or minus, plus and minus, I shouldn't use or, plus and minus. It means that somehow at this location we have maintained a DC power supply. What was the technology behind operating this power supply is none of our business for the time being. This might be available, this might be made available from an actual battery. This might be two connection points out of a potential divider circuit. This might be a connection point out of an AC to DC converter, by full wave rectification and circuit smooth and capacitor smoothing. These two circular things, which are now working as the energy source for the electrical circuit, might be made available in quite a lot of different processes. But how does that work, or the existence of those whole mechanism need not be shown on the circuit. We have these two circuit symbols, the two circles with the label plus and minus, means this is working as our source, and we can simply complete and create and draw our source, draw the rest of our circuit using that one as our source, and it doesn't have to be closed on any point. So that's the important bit for the DC circuit symbol. which we have over here, right over here. This is this circuit symbol, and if you have power AC power supply, we have the same symbol, only that in the middle we have a snake kind of thing. This is basically a small representation of a one full cycle of a sine curve. You can see that this is how a sine curve usually looks like, or you can say it's a worm, however it makes sense to you. This is some symbol for AC. This is a circuit symbol for a transformer. Transformers are electromagnetic devices which works with induction. We're gonna see about them later. It's in our syllabus. We have ammeter, milliammeter, voltmeter. We can also have millivoltmeter. We have fixed resistor. This is the important bit. Have a look. Fixed resistor means the resistors which are going to maintain their resistance at a constant value no matter what. And whenever I say no matter what, I mean it by word. No matter what. Temperature, pressure, hammering, or whatever, voltage, current, none of these things is going to make any value change to the value of a fixed resistor. A fixed resistor means it's a fixed resistor. No matter what, it will always maintain that resistance. Now, whether it is a theoretical concept or it is a practically available idea or available component, that's a different issue that I'm going to talk to you about later. But what I want you to understand that fixed resistor means it will have a fixed resistor. For example, in your circuit, if you are given a symbol like this, I mean, this is have a look. This is a rectangle, basically rectangle with two wires on the two sides. But important not to mess it up with the fuse. Have a look on the very right side. They intentionally gave the fuse sign over here so that you can compare these two things. Do you see the difference between the fixed resistor and the fuse? Do you see it?
Yes, sir.
What's the difference?
The line goes through the rectangle.
Exactly. The line goes through the rectangle. এক মিনিট পোলাবান এই কেমন স্বামী তোমাদের ব্যাচে না?
Yes, sir.
এই কই আজকে তার
Ashin
বার্থডে?
aski.
ওকে বলুন জাস্ট সেকেন্ড ময়লা আসছে মানে ময়লাওয়ালা আসছে ময়লা দিতে হবে আসতেছি অলরাইট সো have a look at the difference between the fixed resistor and the circuit breaker. So fixed resistor is a fixed resistor means it will maintain its resistance no matter what. So if it's labeled let's say 10 ohm, it's gonna be 10 ohm forever. Nothing will change its resistance. But it's fixed resistor that is actually a significantly theoretical idea because physically speaking, any object's resistance is always dependent on its temperature. There are two type of things which are called PTC or NTCs. PTCs are called positive temperature coefficient and NTCs are called negative temperature coefficient. They basically means one thing. PTCs are those which has a rise in their resistance with temperature increase. I mean more less. And NTCs are which have a negative temperature coefficient. It means they have a lowering of their resistance as temperature increases. So more less more, something like that. So you don't have to know the PTC or the NTC term. I'm just telling you these things because these are very adjacent terms which are not included in the syllabus, but at any time I feel like that the examiners might use them just to allow you some possible scope to clear out your hair. I don't know. So that's the difference. There's the fixed resistor, either fixed resistor, and the fuse in the circuit breaker looks like this, which is a rectangle over here. The reason I'm telling you that I'm trying to teach you the symbol for fixed resistor and circuit breaker at the same time because of one thing. In many cases, students do this. Let's say the question has asked the student to draw a circuit. So what they did is that they drew the battery well, then they drew the switch well. Sorry, not this one. And then do the switch well, and then they are asked to draw some components, and then they drew it, and then they completed the circuit. Let's say this is the circuit that they draw. Now they suddenly find out that within the circuit they were supposed to add a resistor. In many cases what they do draw the resistor, but they do not rub off the circuit line well. Some people don't even bother to write it. So if you just draw a circuit or a resistor over here, does this become a resistor? I mean, drawing a rectangle, does this mean, is this a resistor?
No, sir.
This is not a resistor. What is this? This is a fuse. So, but you are not asked. You are not asked to draw a fuse. You are asked to draw a resistor. And so, if you don't rub off a certain part of the conducting wires of the circuit, then you are in trouble. Some people don't forget to rub it, and there are more people than that. I mean, that's pretty rare. quite rare, not pretty rare, quite rare. But there are certain people who rub it, but not with care. So they just rub it with a very little bit. So I cannot actually rub it less over here, but let me just show you that. Maybe they leave a little bit of trace of this line over here, and within this line, above this line, they draw this rectangle to represent the resistor. Once again, this line is not properly rubbed off. It's still visible. So this can be still the examiner, if they want, they can still consider this to be a fuse, and you are not asked to draw a fuse, you are asked to draw a resistor. So you might as well lose mark. So that's the important bit, that if you are trying to introduce a resistor in a circuit which you did not introduce while you are initially drawing it, rub off the pencil line of the cutting wire carefully and with pressure. Don't tear off your paper. I mean, don't be a monster. You're not having a fight with the paper. You're just trying to rub off the pencil mark carefully and completely. So that's a very important thing. এটার জন্য স্টুডেন্টদের সার্কিট ড্রয়িং এ অনেক সময় অনেক মার্ক যায়, because they are not careful for this. It's not that they don't know this. They know this very well, but just because they were careless, they lose this mark. So I want you guys to be not careless about it. And then we have variable resistors. Variable resistors can be drawn in this two fashion. I'll tell you how they look physically. They both have pretty much the same purpose, but one of the variable resistor that only has two connection wires over here. Actually, let me draw it over here. The variable resistor that is drawn in this manner with one resistor and one arrow. You should understand, in electrical circuitry there are certain notions which actually works empirically. Empirically means it works same everywhere. This kind of an inclined line represents something is variable. For example, this is a variable resistor. Although you haven't come across it, but you might. This is a fixed DC source. But if I just draw it like this is a variable DC source. Variable DC source means that you can, by the turn of a knob or by the pressing of some digital buttons, you can change the voltage value across these 2 points, whereas this one cannot be changed. So this kind of an inclined arrow in electrical circuits in many cases can represent a variability option. Similarly, double arrows mean light. In electrical circuit symbols, double arrows mean light, which you're going to see in a bit. I mean, whenever we have an LDR stands for what? Light dependent resistor. So light has to fall onto it for its property change. This is not going to emit light. So LDRs are drawn like this. Light is falling on the resistor. That's the symbol. This is the symbol for an LDR. Whereas we have LEDs, which are light emitting diodes. So they're practically diodes. This is the basic circuit symbol for a diode. Diode is basically an electrical component that can allow the current flow in one direction and not on the reverse direction. So this will allow conventional current in this way perfectly, and this will stop conventional current in this way completely. That's how a diode works. Easier way to remember that this is how a diode looks. It's an arrow with a sort of like a gate in front. Whenever the way I used to remember it, that whenever current is trying to flow in the direction of the arrow, conventional current will be able to go. But if the current is trying to go in the other way back, current will be stopped. So the diode works like a closed switch in the forward bias. I mean, current attempting to go in this direction is what we call forward bias, and current works, and the diode works like an open switch or offers infinite resistance. It doesn't allow any current to flow through. In the reverse bias, that is when the current is trying to flow in the opposite direction. So this is the circuit symbol for a diode. The LED, which is the light emitting diode, is basically a diode with an optional circle. The circle is optional, and 2 arrows coming out. This one can be the circuit symbol for an LED, or if you want to skip the circle, you can directly just draw the diode and draw 2 arrows coming out of it. This is the circuit symbol for a diode. Here, these double arrows are representing light. In coming into the resistance makes it LDR. Going out of the diode makes it LED. Not to confuse stuffs. Difference-টা খেয়াল করো, বুঝা যাচ্ছে কি?
Yes, sir.
ঠিক আছে? So এগুলা ইম্পর্টেন্ট জিনিস। এই তো এগুলা গেল। Then heater elements are shown like this. Acha, variable resistor we have. Oh, acha, in many of the cases in the variable resistor. So let me take a bit more time for the variable resistor. This is the type of variable resistor that we use most commonly in our regular life purpose. For example, the most common use for variable resistor in our regular life is the regulator of the fan. For those who have fans in your house, you might as well have a regulator in the switchboard. And what you should see in those switchboards is that if you rotate, we can rotate the switchboard to increase the speed or decrease the speed of the fan. The idea is very simple. This is a variable resistor, and whenever we put the fan speed to highest, we actually set the variable resistor resistance to the lowest, which means the regulator, which is basically a variable resistor, that does not offer any resistance to the basic flow of current to the fan. As a result, the fan runs at its maximum speed. Now, if we start to slowly increase the resistance, then the introduced resistance from the variable resistor or the regulator of the fan is going to lower down the current value, because it's going to limit the current value, because it's going to offer more obstruction in the flow of current. That's what I said for the definition of resistance. And as a result, the current value will drop, and that will cause the fan to run a bit more slowly. So that's the basic purpose of this kind of variable resistor. That's one thing. And another circuit symbol for the variable resistor is this one. This is the most common type of variable resistor or the resistor that we use in our labs. I'm going to explain how this thing works very detailed with the help of some picture. So this is something that you also need to understand. Did you kids ever have your hands on a variable resistor in ever? Like, did you ever touch them?
Regulated, let's see.
Yeah, fan regulator, but I'm talking about, I'm trying to show you, I'm trying to talk about that. Let me just show you. Variable resistors are also called rheostat. Rheostat is just a fancy name for those things. Have you kids ever grabbed any of these devices? Ever? Not yet. It's okay if you say no. I just want to know whether you have used it or not.
Sir.
Acha. This is the most common type of variable resistor that we use in our laboratory purposes. This is the most common type of use. And here, this is actually, I can actually use that. Or maybe I'll use this image to explain. This is a very large image, 2000 by 2000. Yes, this is a good one. Let's copy this, take it, and it's gonna be a huge image. Oh no. Achha. This is the most common circuit. This is the most common type of design for laboratory-based rheostat. I'll explain how this works. On the two sides, you can see two aluminum frames. This one, which has a leg, and this one, which has a leg. These things are optionally made from metal. These are made from metal because of more sturdiness or long-lasting thing, but they can be very well made from plastic. Most of the variable resistors that you might actually see in your laboratories, these legs are made of plastic. Here, for example, here they are made of plastic. Here these legs are made of plastic. So plastic is more common than metal because plastics are cheap and they also pretty much serve the same purpose. That's the first thing. This is the constructional part, and then within these holders or support system, we have a non-metallic cylindrical object, which is this white plastic cylinder. Do you see that? It runs to this whole thing. This one and also this one. Like this.
Yes, sir.
Yes, it's a long, and it is obviously and compulsorily it is made from a non-conductor material. It can be plastic, it can be rubber, it can be wood, it could be anything. Then we have two pieces of stainless steel plate which are connected on two sides, and in between those two sides we have a very long resistance wire that is wound in circles like this, and these wire are wound in such a way they are actually touching side by side, pretty much like if you close the fingers of your hand. I mean, don't, or if you try to if you are about to make a fist, but don't make a fist. If you just touch all the fingers of one hand side by side, the way they are touching each other and they are aligned, they're all parallel and they are not overlapping each other. That's basically how all of these wires are aligned over here. They're all touching each other. All of these wires are insulated. So they are not laterally connected electrically to each other. So there is no electrical connection from, I mean, you have to understand that these wires are all insulated, means if you feed current through one path, it has to go through the whole coil wire eventually to come out over here. I mean, there is no way it can transfer from here to here and maybe transfer from here to here, here to here. Lateral transformation will not happen. Do you understand my point?
Yes, sir.
বলো এই কথাটা বুঝো, এই কথাটা খুব ইম্পর্টেন্ট। কারেন্ট আমাদের একটা ওয়্যার থেকে আরেকটা ওয়্যারে horizontally thickness এর মধ্যে দিয়ে পাস করে যাবে না, because they are all insulated. However, the insulation is actually quite thin, which brings us to the next benefit of this clamp or this clamp or this clamp or maybe this one or maybe this one. আচ্ছা, এইটা অ্যাকচুয়ালি আমার খুব একটা ইয়া না, কারণ হচ্ছে আমরা টিপিক্যালি ল্যাবে এরকম ইউজ করি না। আমাদের টিপিক্যালি ল্যাবের ইকুইপমেন্ট দে লুক মোর লাইক more or less look like this, obviously with plastic borders or something like that. আচ্ছা, this will also work, not a big deal. আচ্ছা, বলতেছে এখানে কি হচ্ছে, I'm trying to look for a very specific design which I cannot find, but I believe we can work. Yes, this is the design that I was looking for. Yep. So why am I looking for this? I want all of you to understand and see and have a look over here. Over here you can see a metal rod, this rectangular rod that you can see over here. Let me copy this so that I can actually rub on it. Okay, so this is a rectangular rod which is made from metal. This one is made from metal, and you can see over here we have 3 connection points. This is one of our connection point, this is one of our connection point. I'm showing these things by circles because I just told you that circles mean connection points. These are the 3 connection points of this electrical equipment. How does this thing work? This is what I want you to understand. This silver side, the stainless steel side wire is connected to the left end of this long resistance wire. This long resistance wire, I mean this shadowed part that you can see over here is actually this kind of wire which are wrapped one beside another one. So these are pretty thin, that's why it's looking like a shadow or shade, but that's how they work. So we have all of these wires over here. So the left end is electrically connected with this screw and the right end is electrically connected with this screw underneath, and as a result we can use these 2 connection points to connect 2 circuits. In between these 2 points, the resistance is the entire length of the resistance that is offered for in between these 2 points is the total resistance of the wire, because the entire wire in highly coiled form is connected across these 2 points. Does this make sense? বলুন, এই কথাটা খেয়াল করো, এই ওয়্যারের লেফট সাইড এই স্ক্রুর সাথে লাগানো, এই সেম ওয়্যারের রাইট সাইড এই স্ক্রুর সাথে লাগানো, তার মানে এই 2টা পয়েন্টের অ্যাক্রসে রেজিস্ট্যান্সটা হচ্ছে পুরো ওয়্যারের রেজিস্ট্যান্স, ঠিক কিনা? মানে হচ্ছে আমি যদি এখান থেকে একটা সার্টেন ব্যাটারি কানেক্ট করি এবং লেটস সে কনভেনশনাল কারেন্ট কামস আউট অফ দ্য পজিটিভ এন্ড এন্ড ইট ফ্লোস থ্রু দিস ব্যাটারি, এই কারেন্টটাকে কি করতে হবে, এই পুরাটুকু ভিতর দিয়ে বন 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 করে পুরো ভিতর দিয়ে ঘুরে আলটিমেটলি এখান দিয়ে বের হয়ে এসে তারপর আমার ব্যাটারিতে ব্যাক করতে হবে, ঠিক না?
Yes, sir.
তো তার মানে কি এখন আমার সার্কিটের ইফেক্টিভ রেজিস্ট্যান্স কি, এই পুরো ওয়্যারের যে রেজিস্ট্যান্স এই পুরোটুকুই তো অ্যাপ্লিকেবল হবে, ঠিক কিনা?
Yes, sir.
বাকি সবাই এটি বুঝছো কি বলতেছি আমি?
জি স্যার।
সো একটা রিওস্টেটের গায়ে যদি একটা এরকম জিনিস লেখা থাকে, আমার একটা রিওস্টেটের গায়ে লেখা আছে হচ্ছে 200 ওহম, আর কিছু লেখা নাই, শুধু 200 ওহম লেখা, এটা মানে হচ্ছে the maximum resistance that this resistor can offer you is 200 ohm. তার মানে হচ্ছে আমার এই 2 পয়েন্টের মাঝখানে রেজিস্ট্যান্সের ভ্যালু হচ্ছে 200 ohm. The maximum resistance that the resistor can offer is 200 ohm. The minimum resistance any resistor can offer is always 0 ohm. So practically the range would be, even if the 0 is not mentioned, the practical range is 0 থেকে 200 ohm. 0 to 200 ohm. That's the basic idea. So connecting across these 2 points, we can get a 200 ohm resistor, no big deal. But that doesn't actually give us a variable resistor. So how do we get the variable resistor? The variable resistor can be like this. Let me try to show you. To make this circuit in a viable resistor format, we have to consider this point. Have a look. This black thing that you can see with a little bit of hand gripping design over here for easier gripping. They have a copper teeth which is touching over here. And there are actually two copper teeth on two sides which are pressing against the wrapping of the wire onto this thing. Now, one thing you have to understand, this copper teeth and one that is on the back, the same thing, it is actually symmetrical. Can I have a top view? I do not see a top view. There you are. So you can see over here that we have actually two of these wires which are pressing against this coil. So this is equally applicable for other figures as well. So here we cannot see the other one because this is actually pretty small, but for this design, they had it pretty large. So what is happening? We have within this wire, there is one copper tip pressing on this side of the wrapping, and the other one is on the other side. The pressure of this copper tooth actually removes a small amount of insulation from the top of the wires. Now, this is the part that I want you to understand. আমি একটা জিনিস এঁকে দেখাচ্ছি, এই জিনিসটা একটু বোঝার চেষ্টা করো। বলবান, মনে করো আমাদের এখানে যে ওয়্যারের যে র্যাপিংগুলো আছে, ওয়্যারের র্যাপিংগুলো হচ্ছে এরকম। মনে করো এটা হচ্ছে আমাদের মেটাল ওয়্যার, এটা হচ্ছে লিড মানে হচ্ছে মেটাল পিস। আর এই ব্লুটা মনে করো হচ্ছে ইনসুলেশন। এই ব্লুটা মনে করা হচ্ছে ইনসুলেশন। এখন নরমালি আমাদের এই ইনসুলেশন পুরোটার উপরে র্যাপ করে দেওয়া আছে। আমি পুরোটুকুতে ব্লু দেখাচ্ছি না তোমাদেরকে বোঝানোর জন্য। এখন মনে করো here I have tried to show you 4 different wires which are placed side by side. The red wires, the red lines are representing the actual wires, the metallic parts, and the blue parts represent the insulation. What happens when this copper teeth actually rubs along a pathway like this? Let's say I'm going to show you that this path, I mean this path over here. Let's say when the copper wire rubs along this path, it actually removes a little bit of insulation on top over here, a little bit of insulation on the top over here, and a little bit of insulation on the top over here. However, the insulation in between the two wires, that pretty much remains the same, which means the wires becomes exposed on their tops, on their surface side, not on their inside. এই পার্টটা কি বুঝতেছো? বলবান, these wires are gonna lose a small part of the insulation in the location where the copper teeth is rubbing across them, which means on the face side a little bit of insulation would get removed, but the insulation between the two wires, this insulation would pretty much remain same. Try to think about it. I mean, the idea is that what I want you to understand that, let's say, try to I cannot show you, I wish this was a physical class. Press the 4 fingers other than thumb of your left hand and try to look at them. Now, the fingers are touching each other. Are the bones touching each other of your fingers? No, the bones are not touching each other. Now, the way this copper teeth works is that, let's say, if you keep your fingers in this manner and someone brings up a file, or do you guys know what a file is? It's just a thing by which you rub off stuffs, you remove material or some heavy object, and then they rub across your fingers in a straight line multiple times and expose your bones. Your fingers would still be touching each other and the bones would not touch laterally side by side, but the part where the flesh might be removed, those parts the bones can be exposed, right? This
Yes,
is
sir.
a good example, but I think it works because you can see it. You can visualize it easily. So that's pretty much what happens for this part of the coil, is that by the rubbing of the copper teeth, it actually removes a small bit of insulation on the surface and can make actual electrical contact with the inside wires. However, the wires remain insulated from side to side because the copper teeth only removes the insulation on the top portion. It doesn't remove any insulation for the in-between wires. The in-between wires insulation is still intact in between very well. এই পার্টটা কি বুঝতেছো কি হচ্ছে? বলবান এটা তোমাদেরকে এত মানে বোঝানোর মেইন রিজনটা হচ্ছে যে if I just a bit of okay. What happens if you want to use this as a variable resistor or a rheostat, we have to choose any of these two outlets and we must choose this outlet. এখন মনে করো আমি তোমাদের একটা এক্সাম্পল দেখাই। মনে করো আমি এখান থেকে একটা ব্যাটারি রাখলাম, এই ব্যাটারির সাথে একটা এন্ড এখানে কানেক্ট করলাম, এখানে একটা মনে করো বাল্ব দিলাম, একটা ক্লোজ সুইচ দিলাম এবং আরেকটা ওয়্যারকে আমি এখান থেকে বের করে আনলাম। একটা জিনিস খেয়াল করো, এখানে কি হচ্ছে, এটা হচ্ছে আমাদের একটা মনে করো কনভেনশনাল সার্কিট। কারেন্টটি আমাদের এই জিনিসটা এখানে আসছে, মানে কারেন্ট আমাদের এখান থেকে ঢুকতে হবে, কারণ এদিক দিয়ে পজিটিভ এন্ড থেকে বের হবে, কনভেনশনাল কারেন্ট পজিটিভ এন্ড থেকে বের হবে, বের হয়ে এসে এই স্ক্রু দিয়ে এসে এই স্টিল প্লেটটাতে আসবে। তারপর এখান থেকে সেই পুরো কারেন্টটা এখান থেকে এইখান দিয়ে ঘুরতে 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 যখনই এই পয়েন্টে আসবে তখন সে কিন্তু এদিকে যাবে না, কারণ কারেন্টের কিন্তু এদিক দিয়ে বের হয়ে যাওয়ার কোনো রাস্তা নাই। The current doesn't have an open path to leave out from here. Rather, the current is going to climb through this copper teeth and eventually which will be entering this rectangular rod, and then the current is going to flow through this rod conveniently and eventually it's going to complete its journey through the bulb and come back to the cell once again. Pathwayটা খেয়াল করো, এই does the pathway sound acceptable? Why did the current why could the current actually enter through the copper teeth? That's why I tried to explain it that over here, that by the rubbing of the copper teeth, a little bit of insulation of the resistance wire get removed. Through that contact points, the current can actually travel from here and eventually travel up there and eventually go out and eventually come back over here. এই আইডিয়াটা বুঝা গেছে কিনা? হ্যালো,
Yes, sir.
আচ্ছা কারো কোনো কনফিউশন থাকলে আমাকে বলো বা চ্যাটে লিখো, ভালো হয়। আচ্ছা, so what I wanted to understand that in this case, I told you a bit earlier that let's assume this rheostat was labeled as 200 ohms, which means this is a symbol for ohm, which is a unit for resistance. It's labeled as 200 ohm, which means the total resistance across the entire length of wire is 200 ohm. Now what will happen, by grabbing onto this thing by physically, we can actually move it left or right. One of the important thing that you have to understand, which is a rule of thumb, is that for the sake of simplicity or for a much generalized case, we consider the connecting wires to have zero resistance. All the connecting wires other than the components mentioned in the circuit, they all will have zero resistance, which means this connecting wire, this connecting rod, this connecting wire, not the bulb, this connecting wire, they all have zero resistance, which means they are not going to consume any energy out of the charges that flow through them. They are going to allow the flow of charge without consuming any energy out of the charges. I mean, one of the physical way that you can visualize this path is like a frictionless track. If you have a frictionless track that is, let's say, infinitely long, and if you put an object onto this surface and give it a little bit of push, like else even the slightest bit of push, and the object starts moving. Now, because it is a frictionless track, this motion is supposed to sustain forever. ঠিক না? এই জিনিসটা কি বুঝো বলবান? Sure. Let's say there is a frictionless track. There is a long path which of zero friction, someone made it for you, or you just have it accessible for you. And then you place a certain object on the frictionless track, and you give it a little bit of push, and it ever so slightly, and it starts moving forward. Now logic tells us that because this object is moving on a frictionless track, this movement is supposed to sustain forever. This object will keep on moving in that track forever. Now, is it acceptable in your understanding?
If we exclude air resistance, yeah, then it's possible.
Okay, we don't have any of the resistive forces. Air resistance is not present, frictional forces are not present. I mean, there is no way you're going to extract energy out of that object. I mean, the object is going to be able to maintain its total energy within itself. That's the idea. So if that's the case, then this object is supposed to be moving forever. Am I correct?
Yes, sir.
এটা কি সবাই accept করতে পারছো? I mean, having the idea of something is moving for eternity on its own doesn't seem right, but it is very much possible. Already you have to understand that why does anything comes to a stop? Whenever something loses kinetic energy, it comes to stop. Why does something loses kinetic energy? Because some other forces works against it and slowly starts to take away kinetic energy out of the object. If we remove all of those entities which are supposed to provide some sort of hindrance towards the move against the movement of an object, then we can essentially make the object hold on to all of its kinetic energy for an indefinite period of time. And that would essentially mean the object would be in motion with the same velocity for an indefinite period of time. So এই কথাটা আমি তোমাদেরকে এজন্য বলতেছি যে in the same way an object moving over a frictionless track can keep its motion forever without losing any energy. In electricity, we consider connecting wires to be of similar pathways for charges. When charges will flow through connecting wires, they will spend no energy whatsoever. They will only spend energy in definitive electrical components like bulb, like a diode, like an LDR, like a heating element, like a rheostat. These, when they're flowing through a connecting component or connecting wire or connecting rod, they will lose no energy whatsoever. So the point that I'm trying to make is that in this case, whenever the current is going to flow through here, the current has to go through all of this left part of the coil, and then they're going to find out this copper teeth, and they're going to jump through here and flow through this connecting rod, which is a very large rod having almost zero resistance, and eventually it's going to flow through the connecting wire and flow through the bulb and eventually come back to the battery. Now this rheostat in this current state is offering this much resistance within the circuit because the current has to flow through this much length of resistance wire. We can increase this resistance simply by grabbing onto this thing, and if you move it a little bit to the right, if you push this thing a little bit to the right, what's going to happen?
The wires get contracted.
Which wires?
So get compressed.
No. These were, I mean, these wires which are here,
Yeah.
these wires are not getting compressed. These wires are just a wrapping. Let me just show you other better pictures maybe. They are just wrapped around wires on a cylinder. But they are very thin wires. That is the problem. That's why I cannot actually show you the wires to that level of detail. Acha, this might be a better thing for you to understand. Have a look. You can now see all of these wires individually. Do you see that?
Yes, sir.
Hold on, দেখো তো এই ইমেজটা দেখো তো। এই ইমেজে সবগুলো ওয়্যার individually wrap করা, and they are not touching each other. Do you see that? Now the thing is, these wires, maybe these wires are bare wires. Bare means they don't have insulation. They might have insulation for all I care, but over here a very small length of wire could give us 110 ohms, and the total resistance from this end all the way to this end is a total of 110 ohm. Now this is what is happening over here, and if you want to accommodate even a longer amount of wire, then what do you have to do? You have to reduce this gap, right? And you have to introduce more coils of turn. So if you wrap them with such closeness, then basically what you get is what we have over here, a shaded coil of wire, which is basically like this. Here the wires were a bit more thicker, that's why they are visible better. But here the wires were, for this device the wires were even thinner, that's why it apparently looks like a shade. But they are individually wrapped coil. বুঝছো কি বলছি? একেম সামি, হ্যাপি বার্থডে।
থ্যাংক ইউ স্যার।
ওয়েলকাম। আচ্ছা, এটা কি বুঝছো এই এই সার্কুলার এই কি বলে এই র্যাপিং এর পার্টটা কি বুঝে গেছে আসিফ?
Yes, sir.
আচ্ছা, কার কোনো কোশ্চেন থাকলে বলো। So what I was trying to say that if we now move the resistor from this point to a bit more right, then what's going to happen? I'm going to use, let's say, different color, green, to make sense. If we now move the resistor over here so that this copper teeth is going to touch the resistor light right over here, and the whole thing is over here as well, as the whole rectangle thing is now over here, we have moved it, then what's going to happen? Current is going to come out through this pathway, it's going to enter through this screw and through this stainless steel plate, and it's going to start going around in this coil. It's going to keep on going, and eventually when it's going to hit this copper teeth, and then it's going to flow through this box and go up to this rod, and then flow out of this rod, and eventually flow back all the way up to the bulb and into the battery. Now, what I want you to understand, whenever we move the resistor a little bit to the right, we introduced a longer part of this resistance wire into the circuit, right? Earlier, a smaller black length part was introduced into the circuit, but currently the green length of the resistance wire is introduced in the circuit. So essentially, for which of this case, the resistor will give you a bigger resistance? The black one case, I mean, for this position, let's say position left, or this position right. For which position of the resistor should you have a bigger resistance introduced in the circuit? Which one do you think? And you're allowed to do mistakes. Just respond. I'll help you understand.
To the right one.
The right one is a response from one of your friends. Anyone else?
It's the left one.
Okay, left one is also a response. Anyone else? The question is, for which of the position of the rheostat, left or right, does the rheostat, this whole thing, introduces a bigger resistance into this whole circuit? And for which position of the rheostat, this thing is actually called a jockey because it can slide. So for which position of the jockey do we have more effective resistance for the circuit? That was the question.
Right.
Okay. Anyone else want to enlighten us? No. Okay. The correct response is right. I'll tell you why. Because আচ্ছা, রেজিস্ট্যান্সের ডিপেন্ডেন্সি গুলো তো তোমাদেরকে এখনো পড়াই নাই, এই জন্য হচ্ছে তোমাদের এই জিনিসটা ধরতে কষ্ট হচ্ছে। Resistance of a certain wire depends upon two primary factors. Resistance is directly proportional to length. Resistance is inversely proportional to cross sectional area. এটা ইন ডিটেইলস তোমাদেরকে পরে আবার পড়াবো, কারণ এটা নিয়ে আমাদের প্রপোর্শনালিটি অনেকগুলো ম্যাচ করতে হয়, বাট আপাতত জাস্ট বোঝানোর জন্য বলতেছি। Resistance is directly proportional to length. This essentially means that if you have identical pieces of wires, one is small and the other one is longer, the one that is longer will definitely have a bigger resistance, provided that they are both made from the same material and they have the same cross-sectional area. So if they are same in their physical attribute, then the one that is longer will always have a bigger resistance, because whenever the wire is longer, then the electrons or the charges have to go through this obstructive path for a longer distance. So the amount of hindrance would become even more. So এই প্রশ্নটা তোমরা এখন শিখো নাই, সো ওই জন্য তোমাদের এটা অনেকে একজন লেফট বলছিলা, but what I wanted to understand that whenever we introduce a longer length of resistance in the circuit, the bigger the amount of resistance would be introducing into the circuit. তার মানে হচ্ছে যখন এই কেসে যেহেতু আমরা অলরেডি লেফট এটাতে কানেক্ট করছি, নাও if we start to move it to the right, essentially we will be introducing a bigger resistance into the circuit. If we now move the rheostat all the way to the right and ultimately bring the copper teeth, can I draw with this one? Ultimately bring the copper teeth, which is this one. Ultimately, if we bring the copper teeth right onto this plate, then what should be the resistance of the rheostat? What would be the effective resistance of the rheostat that will be introduced in the circuit? আমরা যদি এই স্লাইডারটাকে জকিটাকে একদম ডান দিকে সরাই, মানে পুরোপুরি ডান দিকে সরাই একদম এখানে নিয়ে আসি,
Maximum resistance.
And that is
200 amperes.
ohms. Good. So in that case, the current has to flow through the entire length of the wire, and eventually after finishing go through all the wire, this will go through here. So what I want you to understand that this is the variable N for us. I mean, although we are going to connect our wire physically with this screw, but being able to slide this black thing, the jockey, this actually work for us as a variable connection option. By moving this slider, we can choose where this copper teeth, the copper teeth is no longer visible because of my drawing, but you can see it over here a little bit, or maybe I can paste another version. Oh, not this one.
So what is the rod made up of?
Sorry?
So what is the rod made up of? Where the rheostat is situated, the rod.
A second. This rod is usually made from brass, or it can be also made from basic cast iron with a little bit of nickel plating. It is a pretty thick rod in terms of metal, and you can see over here the resistance was also inversely proportional to cross-section area. So whenever we have a pretty thick rod, this can offer very little resistance. I mean, it has enough electrons to allow a very large amount of current flow. বুঝছো কি বলছি?
Yes, sir.
আচ্ছা. So that was the case for this figure where we had so the point I was trying to make is that the position of this copper teeth, which is basically what you define as the jockey, actually tells us how this circuit is going to work. Now if I try to redraw the circuit one more time, here we had a bulb, so and we had a closed switch, and this wire was connected to this end. And now, as you can see in the circuit, the resistance of this rheostat was between this point and the slider. এটুকু হচ্ছে আমাদের effective resistance. If we now move it to the right, we'll introduce more resistance. If we move it to the left, we'll introduce less resistance. ঘটনা কি এটাই কিনা? এই আইডিয়াটা বুঝছো কি সবাই?
Yes, sir.
Everyone.
Yes, sir.
এটা একটু বুঝো, এটা না বুঝলে পরে ম্যাচ করতে কষ্ট হবে, বা হচ্ছে ল্যাব করতে গিয়ে আরো কষ্ট হবে. So if you can, এটা হচ্ছে situation. And now if I move it all the way to the left, and if you bring this copper teeth right over here, the resistance offered from the variable resistor will become 0. The more you move it to the right, the bigger resistance you're going to be applying, and whatever the biggest amount of resistance is labeled over here, that is available at the very last end. Vice versa, অনেক সময় আবার এরকমও হতে পারে, আমি তাদেরকে আরেকটা সার্কিট এঁকে দেখাচ্ছি। আমি অনেকগুলো সার্কিট রাখতেছি কারণ তোমাদের পুরো জিনিসটা অল টুগেদার বোঝানো দরকার। ওকে, আরেকটা জিনিস দেখো, সেটা হচ্ছে what if I connected one end of the circuit over here and then connected the battery, bulb, a closed switch, and then connected over here. এখন সিচুয়েশনটা কিরকম হবে বলো তো? Try to visualize the path of the current as the current will complete the circuit. Let me help. Current comes out of the positive end, goes here, comes here. Then what the current is gonna do? Is it gonna go in which direction the current will flow?
It's in the left direction.
It is gonna flow to the left, and try to stop me whenever it is supposed to not keep on going left anymore.
Right, sir.
So what's gonna happen now?
It's gonna move up the jockey and move
It's
to the
gonna
left
move
side.
the jockey, flow through the connecting rod. Beautiful. Thank you very much. Correct response. Beautiful. And it's gonna come back. So in this case, if we now choose this right end to be one of our connection point, and this red one, the red one is a compulsory connection point, which is the sliding point. But between these 2 points, we can choose. In my earlier discussions, I was trying to show you that if you choose the left one, in that case, this is our effective resistance. The left part is our effective resistance. What I'm trying to show you over here, if you choose the right one, then this part is our effective resistance. In this case, moving it to the left is going to give us more resistance. Moving it to the right is going to give us less resistance. ठीक ना? Because
Yes, sir.
it's all about how much length of this variable resistor are you incorporating within the circuit. Is it clear to all of us that how does a variable resistor work? বুঝা গেছে কি সবার?
Yes, sir.
Yes, sir.
All right.
Sir, I have this question.
Sure.
Brass তো conductor না?
Yes, yes.
তাহলে আমরা শক কেন এক্সপেরিয়েন্স করতে পারি না? কারণ কারেন্ট যেহেতু ওটা দিয়ে পাস করছে।
Good question. We human beings sense shock whenever our body, or even maybe a small part of our body, a portion of our body, becomes an active part of a circuit. It means our body works as a conductor. That's when we feel the shock. Now, normally our body is not supposed to work as a conductor, because dry skin, a live human being with dry hands and dry skin, offers a pretty high resistance, like within kilo ohm value. But you have to understand that right beneath our skin we have blood vessels. Blood vessels are filled with blood, and blood happens to be a electrolytic solution, filled up with a lot of ions, metal ions, and other ions as well, radicals and everything. So that electrolytic solution is a very good conductor of electricity. So the point to be understood is that if somehow the resistance that is offered by the skin is penetrated by some charge because of the high voltage, and they can enter into the bloodstream, then they can have a very easy flow path through the bloodstream, and blood goes everywhere in the body, which basically means any part of the body would be accessible for the current to go to. So the question that you asked, that why don't we get a shock? We will get a shock if our skin resistance cannot stop the incoming charges. And this is only going to happen if the charges have a very high voltage, or each coulomb of charge comes with a very large amount of energy, so that they could physically overpower the resistance of our skin and actually enter into the bloodstream. Only then should we get a shock. Typically, for a DC power supply, for example, a 9 volt or 12 volt, this kind of power supply, the voltage is not that good, and the rate of current flow that actually happens to these components are also not that high, that we can have enough sensation of shock. Now, some people might actually sense a bit of tingling sensation within their skin, but I'm saying some people because not everyone has that much sensitive skin. I don't. So some people might sense it a little bit, which is what I would say is the first a very primitive expression of a shock. So if the electricity will first, I mean, if you start sensing the electrical effect, you will first have a bit of tingling. Then this is gonna slowly start, that tingling sensation is gonna slowly convert into pain. So whenever we experience pain out of an electrical experience, that's essentially what we call it to be a shock. Did I answer your question?
Yes, sir.
বুঝা গেছে?
Yes, sir, বুঝেছি।
আচ্ছা, আমরা ঘুরতে ঘুরতে বহুত জায়গায় চলে আসছি। আমরা ডেফিনেশন আলাপ করতেছিলাম। ডেফিনেশন গেল কই? এখানে আমরা ডেফিনেশন আলাপ করার জন্য চেষ্টা করতেছিলাম হচ্ছে ভোল্টেজ ডিফাইন করার জন্য। ভোল্টেজ ডিফাইন করতে গিয়ে আমরা ইলেকট্রিক্যাল সার্কিট সিম্বল আসছে, সার্কিট সিম্বল থেকে আমরা পট করে রেজিস্টারে চলে গিয়ে রেজিস্টারে অনেক কিছু আলাপ করে ফেললাম। আচ্ছা, ঠিক আছে, লেটস গেট ব্যাক টু দ্য পয়েন্ট দ্যাট উই লেফট অফ। I'm going to try to explain the difference between EMF and voltage. The idea is very simple. আচ্ছা, ভোল্টেজের ডেফিনিশন এখানে আমাদের হচ্ছে এনার্জি কনভার্টেড পার চার্জ অর ওয়াট ডান পার চার্জ। আচ্ছা, এখানে আমি একটা জিনিস তোমাদেরকে একটু এঁকে দেখাই। মনে করো if this battery over here is rated as 10 volt and it means 10 joule per coulomb, whenever 1 coulomb charge will come out of this battery, it's going to hold 10 joule within itself. Like I said, connecting wires don't take any energy. It means 1 coulomb charge will take this 10 joule and they're going to keep on flowing through the connecting wire, through the connecting wire, through the connecting wire. It's going to eventually reach up to this end. And now it has to flow through a resistance wire, because this filament is a very long, thin wire, which is designed to do the energy conversion. Now, this 10 coulomb joule 10 coulomb of 1 coulomb charge is going to start flowing through from this end all the way up to this end, and because of the construction of the circuit, it is going to spend all of its 10 joule energy within this path. Now if you wonder why all of it, the reason is very simple, because within this circuit I haven't given any other resistor. If I, let's say, let me use red. If I gave another resistor over here, let's say if I gave another resistor over here, now what you should see that now for the charge, for 1 coulomb charge to pass through the whole circuit, it has to go through one resistor element over here, and then it has to flow through the same path, and it has to go through another resistor element over here. And it started with an amount of 10 joule. It means now 1 coulomb charge, which is containing 10 joule of energy, will spend its energy with a very conspicuous calculation, and it will be defined naturally. It will spend a fraction of its energy on the filament lamp and the remaining energy onto the resistor. If it's, let's say, if it spends, let's say, 8.3 joule of energy on the filament, then it's going to spend this remaining 1.7 joule in the resistor. And eventually, as it will leave from the resistor, ultimately it will have 0 joule. Now you might wonder, how does an object with 0 joule move? Well, that's the that's the catch. Objects with this 0 joule doesn't necessarily mean absolute zero. The electrons or the charge is still moving, but they don't have any more expendable energy. They started with 10 joule of expendable energy. Within the circuit, they spent that extra 10 joule of energy, and as they come out of the last equipment, they don't have any energy left. All that they will do, they're going to flow through this frictionless track or zero resistance wire. They're going to flow through the switch and eventually get absorbed in the battery once again. That's how the energy conversion of a circuit basically works. The charge that it has to pass through all the electrical components, it spends energy in those electrical components, and eventually it comes back to the original source. এই কনসেপ্টটা বুঝা গেছে কিনা? Whenever charges come out of the electrical source, be it a battery or DC source, they are gonna come out with the exact rated voltage of the source. For example, in this case, I label the source as 10 volt, so which means 10 joule per coulomb, which means whenever 1 coulomb charge will leave from the battery, that will keep 10 joule energy with the expendable energy, 10 joule electrical energy within itself. And as the charge is gonna flow through the whole circuit, it will automatically determine that how many resistor components, how many resistive component. A resistive component in this case means components which offer a resistance. For example, connecting wire is not a resistive component. It's just a free pass. Connecting wire is not a resistive component, but this filament and this resistor, they are resistive components where you will have to spend some energy, or you have to convert some of your electrical energy into other form of energy to be able to pass through them. So in this case, we have two resistor components. One is the filament, another is the resistor. Automatically, this 1 coulomb charge would know how much energy to spend where, so that once it is out of the last resistor component, which is this point, it will have no expendable energy left. So what I was trying to choose as random numbers is that if it so happens that that 1 coulomb charge gives up 8.3 joule of its electrical energy in the filament, then it's going to flow through this all of this path holding on to 1.7 joule of energy, and then it's going to give up 1.7 joule of energy within the resistor, and as it will come out of here, it is going to come out with 0 joule of expendable energy. বুঝছো কি? আমি জিনিসটাকে আরেকটা ইন্টারেস্টিং ভার্সন দিয়ে দেখাই, তাহলে তোমাদের জিনিসটা বুঝতে আরেকটু সহজ হতে পারে। I'm gonna steal out this picture and take it a bit far away because I need a bit more space around it. আচ্ছা পোলাপান, তোমরা কি ভোল্টমিটারের কনসেপ্ট বুঝো? আচ্ছা, voltmeter concept বলেছি. Voltmeter is basically a device which it has a circuit symbol that looks like this. Let me draw it black, which looks like this. If it is connected, if the two ends of a voltmeter are connected across 2 points of a circuit, it will be able, or it is able to, এক মিনিট বলবো না, আসতেছি আমি। A voltmeter is basically a device which is capable of measuring voltage across 2 points of a circuit. এখন, if I want to give you the idea of voltage in a comparative term, not in its absolute form, because the absolute definition or the core definition of voltage is actually a bit complicated. It's taught in A2 level, not even in AS level. So we're going to work with voltage difference and work with the comparable version of the voltage. If you wonder what I'm trying to talk about, or if you wonder that why am I saying these difficult words, let me just tell you one thing. তোমরা কেমিস্ট্রিতে এনথালপি নামে কিছু পড়ছো?
Yes, sir.
Did you ever come across the statement that the actual enthalpy of an object can never be measured? All that we can do measure is the change of enthalpy.
Yes, sir.
Did you understand that?
আপনি একবার এক্সপ্লেইন করে দেবেন?
Okay, I'll try to explain it in my level of understanding. I'm not guaranteeing that this is the actual true explanation, but this is the best that I understand and that I can try. Enthalpy of an object essentially means the amount of energy, internal energy, that you can possibly extract out of it from its chemical and potential energy sources. Now, atoms being bonded together in molecule form have some energy stored in the bonds. Then we have van der Waals attraction forces. Then other objects can have electrical bonding forces. For example, they can have, for example, the water molecules. They are slightly polar because of the high electronegativity of oxygen atom. So the water molecules do have their attraction, and they do have the van der Waals attraction force, but they also have a little bit of electrical charge based attraction force because of their slight polarity. So whenever we are trying to do a chemical reaction, whenever we are dissociating and reassociating atoms, breaking down atoms, molecules, breaking down molecules and creating molecules, we are essentially feeding some energy, and we are also getting back some energy. How much energy, how much is the total amount of energy that each of these compounds brought into the reaction environment is pretty difficult / impossible to determine from that reaction. মানে জিনিসটা হচ্ছে এরকম যে if I try to give a physical example, মনে করো হচ্ছে এখানে একটা মার্কেট আছে, ঠিক আছে? মার্কেটে মনে করো হচ্ছে 10-12 দেশের বাচ্চারা ব্যবসা করতে আসছে, ঠিক আছে? এখন কে তার পকেটে কত কোটি টাকা নিয়ে আসছে সেটা জানার কোনো উপায় নাই, কিন্তু কে কত টাকার দামের প্রোডাক্ট কিনতেছে সেটা তুমি তাদের মেমো দেখে খুব ইজিলি যে কেউ এটা বাই করতে পারবে। Enthalpy is sort of something like this. You can never exactly know what is the exact true total amount of energy each of these compounds are bringing in the reaction environment. But how much energy exchange are they doing? How much did they give out? And how much did anyone absorb? That you can precisely observe and measure. That's an idea of the enthalpy exchange. Does it make sense? It doesn't make sense. Hold on, কিছু একটা বলো. It does make sense or it doesn't make sense, so that I can do whatever is needed. আমার কথা মনে শোনা যাচ্ছে না?
Yes, it does make sense.
আচ্ছা, in other words, what I can tell you is that আচ্ছা, let me tell you in a different way. মনে করো সমুদ্রের মধ্যে একটা তিমি আছে. There is a whale in the ocean. You have a device that can measure actual mass underwater at the level of the water underneath the ocean, at the level of the sea, where you can measure mass. You have a device that can measure mass using weight or some other mechanism of balance and everything. You have a device that can measure the mass underneath that water level. Now try to understand, if the capability of the device, the maximum mass it can measure is, let's say, 100 kilo, but the whale is, let's say, a couple of 100 tons. So you do not have the methods and means to measure the entire mass of the whale. But if the whale at this point does some poop, which is less than 100 kilo, and if you can gather all of these, you can measure how much is the change of mass of the whale. You do not know how much is the whale have in terms of mass, but you can actually measure how much decrease of mass did the whale have. By observation, by your methods and means, that's possible for you to achieve. Enthalpy was defined in that manner, that the total amount of obtainable energy, total amount of obtainable energy of an object can never be truly measured. However, how much was actually exchanged, that can be measured. This is not a question of whether it exists or not. It is a question of our limitation of how much can we do. We human beings still do not know methods and means to measure the total enthalpy of any physical substance. However, when multiple objects react, by doing appropriate observation of temperature change or luminosity change or sound expression or shock wave measurement, we can, by methods and means that are available to us that we could develop as a species, we can measure how much energy was exchanged. That's what you can measure. But how much total energy was brought to the environment, that is not perfectly calculable by our technology yet. That's the meaning of that sentence. It's a statement of limitation. Does it make sense?
Yes, sir.
Anyway, I'll get back to my topic. Why I was talking to you about enthalpy? Because what I want you to understand, because in the way that the total enthalpy of an object cannot be measured, potential, the actual default version of potential is not that complicated, but it's somewhat complicated. So that's why it's not taught in our O levels. We're still going to work with potential difference. What I want you to understand that the voltmeter is such a device that if we connect the two ends of a voltmeter to two specific points of a circuit, we're going to be able to measure the voltage across this point. Let's say this battery over here is labeled at 10 volt. This battery over here is labeled at 10 volt, which means I'm gonna make it a bit smaller. If I connect a voltmeter across the two ends of a battery, let's say this is my voltmeter 1, what would be the reading of this voltmeter? It is measuring the voltage across this plate and this plate, which is the rated voltage of the battery. So if we connect the voltmeter across the two ends of the battery, the voltmeter reading gonna be exactly as the EMF of the battery, which is 10 volt. এই যে বুঝছো কিনা দেখো।
Yes, sir.
Yes, sir.
ব্যাটারির দুই পাশে ভোল্টেজের ভ্যালু। আচ্ছা, এখন মনে করো সেকেন্ডে একটা ব্যাটারি ভোল্টমিটার নিয়ে আমি যদি এই দুই পয়েন্টের অ্যাক্রসে কানেক্ট করি, এরকম এটা সার্কিটের একটা পয়েন্ট, ফিজিক্যাল পয়েন্ট, এটা সার্কিটের একটা ফিজিক্যাল পয়েন্ট, আমি যদি এখানে একটা ভোল্টমিটার কানেক্ট করি, এই ভোল্টমিটার রিডিং কত হতে পারে?
10 volts.
How? Have a look. This voltmeter is connected between this point and this point. Do we have any energy conversion happening within these 2 points?
No, sir.
This is a simple piece of connecting wire, ঠিক না? এই যে এখান থেকে শুরু করে এই পর্যন্ত, প্র্যাকটিক্যালি এখান থেকে শুরু করে এই পর্যন্ত পুরোটুকু হচ্ছে কি কানেক্টিং ওয়্যার, ঠিক না?
Yes, sir.
By design is কানেক্টিং ওয়্যার। তার মানে এখানে তো কোনো এনার্জি কনভার্সন হচ্ছে না, because this entire thing from the positive end of the battery all the way up to the starting point of the filament, this whole thing is a connecting wire by design of the circuit. So there are no energy conversion happening anywhere within this circuit, which means there are no voltage drop anywhere within this circuit. If we assume, I'm saying if we assume that 1 coulomb of charge starts with 10 joule of energy from this point, it will keep on having 10 joule all the way up to this point. So there is no voltage drop whatsoever, which means that if I connect 2 points over here, or even if I just rub this off, and assuming that the filament lamp works fine even if we break the glass, assuming that if we even connect the voltmeter right over here I'm still gonna get 0 volt because there is no energy conversion that is happening across these 2 points. There is no resistor over here. We don't have any energy conversion, which means that electrically they are the same point. The voltage over here and the voltage over here are practically the same. ঠিক কিনা? Okay, so that's one thing. Now here I told you that let's say 1 coulomb of energy, 1 coulomb of charge is going to spend 8.2 joule over here, which means the voltage drop across this resistive component, the filament, the voltage of this one is 8.3 volt. This tells us a very precise information. If we connect a voltmeter across these two things, মনে করো হচ্ছে আমরা একটা voltmeter কানেক্ট করব, যেটা একটা মাথা হচ্ছে এই জায়গায় নিলাম আর হচ্ছে এখান থেকে নিলাম. If we connect a voltmeter over here, this is a voltmeter 3. If you connect a voltmeter over here, the reading of this voltmeter is going to be 8.3 volt because this is the voltage drop that is happening across the filament lamp. Here, each coulomb of energy had 10 joule. Here, each coulomb of energy has 1.7 joule. So they are spending 8.2 joule over this filament coil, and as a result, this is 8.3 volts. Now, how does that help? Now, one thing you have to understand. আমরা যদি এখন এই দুই পয়েন্ট অ্যাক্রসের ভোল্টেজ হচ্ছে 8.3 ভোল্ট, তার মানে হচ্ছে আমাদের লেফট এবং রাইট. এখন ইলেকট্রনগুলো 1 coulomb of charge is going to flow through this path with 1.7 joule and eventually it's going to come up over here and spin 1 joule over here, which means now if we connect another voltmeter, let's say voltmeter 4, across the two ends of this resistor, the reading of this one is going to be 1.7 volt. And ultimately, it is going to come back over here with 0 thing. এটা হচ্ছে আমাদের voltmeter reading এর একটা এক্সাম্পল দেখালাম না. আমি voltmeter reading এক্সাম্পল তোমাদেরকে এই জন্য দেখালাম, মানে the reason I'm trying to show you this thing is to give you an idea that you can see over here that voltmeter reading 1 happens to be equal to voltmeter reading 3 plus voltmeter reading 4. Do you see that? Check it out. Voltmeter reading 1 was the EMF of the supply, which is 10 volt, and voltmeter reading 3 is the potential drop across filament coil, and voltmeter reading 4 is the potential drop across the resistor. So the sum of V3 plus V4 is equal to V1. There is a very simple way to explain this thing. Batteries or generators or cells or solar cell or thermal cell, these are devices which convert non-electrical energy into electrical energy. These are the devices that we call sources of electrical energy, which creates potential. For these devices, we use the term EMF. And devices which use electrical energy, which means we have to feed them electrical energy and they're going to convert electrical energy into other form of energy. For example, light, it produces light and heat. For example, a fan, it produces sound and physical motion, kinetic energy. For example, loudspeaker, it produces heat and sound. For example, water heater, it produces heat. So in any device that absorbs electrical energy and converts into other forms than electrical energy are called components, or we sometimes use the term load. Load means components which are gonna use electrical energy. So for those components which converts electrical into non-electrical energy, for those components we use the term voltage or potential difference, PD. By definition, they're the same thing. They represent energy per charge. But for sources, we use the term EMF. It is said electromotive force. This has nothing to do with Newton. This is the name. Electromotive force is the name of the quantity. Nothing to do with actual physical force. It is joule per coulomb. And electrical devices which use electrical energy, they are called for them we use the term voltage or PD. Now, the last thing that I want to discuss is that voltage, I mean, within the sources, other form of energy will be converted into electrical energy, which means that if you have a battery, then chemical reaction will convert into electrical energy. If you have a wind turbine, then the kinetic energy of the wind will be converted into wind energy, will be converted into electrical energy. If you have a solar panel, then the light energy of the sun will be converted into electrical energy, so on and so forth. All that these sources do is that they energize the electrons to make their travel across the circuit. And one more thing is also very important. This is something that you would know as a law in your S level, Kirchhoff's law. But what is really important to understand that any electrical component will always work in such a way that it will not become charged in a circuit. Within a circuit, DC circuit, if within a duration it has a 1 ampere current flowing in, it will definitely have 1 ampere flowing out for the exact same duration. If you cut off the flow of current flow in one place, the entire circuit will stop. For example, if I cut off the wire right over here, the entire circuit will stop. This is not going to work. That we're going to have some current flow up to this point, and some current flow will not flow over here. That's not going to happen. If we disconnect any part of the circuit, current flow will stop everywhere at the same time. There is a very nice physical example that I use to explain this thing in a far better idea, which involves a hollow tube and some marbles, which I'm going to cover in our next class because we are 4 minutes over 11 a.m. তোমাদের আজকে কি বার? বৃহস্পতিবার?
Yes, sir.
কালকে শুক্রবার?
Oh, no, sorry, sir. Sir, বুধবার আজকে।